Hello and welcome again to another series of lectures in real analysis. So we start now with a new chapter and discuss further topics in measure and integration theory. So to start, we consider the definition of initial, final, and product sigma algebras. This will pave way to the definition later to product measures. So let's start with a non-empty set. And this will be our index set. A collection of measurable space, y sub I, t sub I, and a collection of functions f sub I from a set x into y sub I for all I in the index set capital I. So here we would like to give a sigma algebra on the domain X, that is the common domain of all these functions, given the sigma algebras on each y sub I. And that would be the initial sigma algebra. So the initial sigma algebra on X generated by the family of functions or the index set of functions f sub I is given by the following. So we will denote this sigma algebra or this initial sigma algebra by sigma of the index collection. And this is defined to be the sigma algebra generated by combining, that is, taking the union of inverse images of the sigma algebras t sub I corresponding to y sub I. And here recall that f inverse of a collection is defined to be the set of all, let's say, inverse images of E, where E is in t sub I. So again, the initial sigma algebra on X generated by a family of functions f sub I is the sigma algebra generated by the union of the inverse images of the sigma algebras t sub I. In the case where we have a single function, so for instance, for a function f from x to y and yt, a measurable space. So you can think of the index set I to consist of only one element. So it's a singleton. Then we denote the initial sigma algebra generated by this singleton function simply by a sigma of f. So we ignore the braces in the notation. And by definition, this is the sigma algebra generated by the inverse image of T. First remark, I would like to point out here that this initial sigma algebra, it can be shown that this is the smallest sigma algebra in such a way that the functions f sub I from x to y sub I is measurable for all I in the index set. You can verify this immediately from the definition of the sigma algebra generated by a set. So you're asked to verify this on your own. So this is the initial sigma algebra. The analogous definition for a final sigma algebra is the following. So here, instead, we consider, let's say, an index family of sigma algebras, and this will be our domain. So here we have measurable spaces, x sub I, sigma sub I, and a function f sub I from x sub I to y. For all I in the index set capital I. Then the final sigma algebra. So this is now a sigma algebra on the codomain, that is the set Y, generated by this index family of collections, index family of functions, is defined as follows. So the notation would be with a subscript F, designating that this is the final sigma algebra. This is defined to be the intersection of all subsets A and Y, such that Fi inverse of A is a subset of, or is an element of sigma sub I. So you take inverse images of subsets of Y, and that if that is in the sigma sub I, this must be in this collection, and then this must be true for all I in the index set. Okay. Well, it can be shown that this is a sigma algebra, and we know that an arbitrary intersection of sigma algebras is again a sigma algebra. So indeed, this defines a sigma algebra on Y. So in this lecture, we will focus mainly on initial sigma algebras, and the corresponding results for the final sigma algebra are given in the exercises of the course notes. So again, we will only focus the discussion on initial sigma algebras. Let us give some examples. So suppose I have a collection of subsets of X. In other words, a subset of the power set of a set X. A subset of X, and let's say, let us consider the indicator function. Okay. And look at the inverse image of the indicator function of a subset S in R. Okay. So depending whether S contains 0 or 1 or both or neither, you can see that this inverse image is either the empty set, the whole set, the set A, or it's a complement. Then from this, we can see that the sigma algebra generated by C is the initial sigma algebra on X, generated by the characteristic functions where A is in C. Because here, if you take the inverse image, you get the set A and C. So therefore, sigma algebras generated by a collection of sets can be expressed as an initial sigma algebra corresponding to indicator functions of sets in the collection. Another examples that we can express restriction sigma algebras in terms of initial sigma algebras. And this will be our next example. So for this, let us consider a measurable space, say X sigma, and a subset E of X. Define the canonical injection I sub E, E from E to X. In other words, this is the identity map, but the domain is in E. Okay, so recall that the restriction sigma algebra on E is denoted by a subscript sigma sub E. This is by definition the intersection of A and E, where A is in sigma. So we just take the intersection of elements in the sigma algebra, sigma, into the subset E. But then you can see immediately that this is the inverse image of the canonical injection I sub E of A. So therefore, this is the same as the inverse image of the sigma algebra, sigma. Since this is a sigma algebra, okay, so this is equal also to sigma of I inverse sigma. And by our definition, this is the sigma algebra generated by the canonical injection. So therefore, restriction sigma algebras can be written as an initial sigma algebra that is generated by the canonical injection from the subset to the whole set X. So these are old examples written in the context of initial sigma algebras. So in terms of generators, we have the following theorem. So let us consider non-empty sets X and I, a function f sub I from X to Y sub I, Y sub I, T sub I, a measurable space, and suppose that the topology, or I should say the sigma algebra T sub I, is generated by some sub-collection I sub I. For all I in the index set capital I. Then the initial sigma algebra generated by this collection of functions is the same as the sigma algebra generated by the union of the inverse images of the generators. So here, T sub I has been replaced by the generator. So in the definition at this, instead of the generator, we have the sigma algebra T sub I. But according to this theorem, we can replace the sigma algebra by the generators. So let us look at the proof. So for simplicity, let us denote the union as follows. So The first step is to show this inclusion. So that is the right-hand side is a subset of the left-hand side. Now, since E is a subset of the union of the inverse images of the sigma algebras T sub I, it follows from the fact that E sub I is a subset of T sub I. And recall that this is by taking the sigma algebras. Okay, so the sigma algebra of E must be also contained in the sigma algebra of the right-hand side. However, by definition, the right-hand side is the initial sigma algebra generated by the collection F sub i's. So this implies that this is a subset of that. So that's one inclusion. For the reverse inclusion, let's start with the fact that particular inverse image of the a generator is contained in E. And this is a subset of a sigma of E, because a sigma of E is the smallest sigma algebra contained in E. So this is valid for any I in the index set capital I. So taking the sigma algebras both sides, we have this relation. So this is okay. We know that this is by an exercise. We can interchange the inverse image and the sigma algebra generation. And this is equal to F sub I inverse of T sub I, since E sub I generates T sub I. And this is again true for I in capital I. So therefore, starting from the left-hand side, and applying this one, but then take note that this is the smallest sigma algebra containing the inverse image, and we have here a particular sigma algebra containing the inverse image. So this one must be a subset of sigma sub E. Again, for all I in capital I. Hence, taking the union, so all the inverse images T sub i's are contained in sigma sub E. So therefore, the union is also contained in sigma sub E. So this is a particular sigma algebra containing the union. Therefore, the sigma algebra generated by this is also a subset of that. And again, I recall that this is the initial sigma algebra generated by this index family of functions. And that's the reverse inclusion that we would like to establish. So once again, in the definition of the sigma algebra, we can replace the sigma algebras in the codomain by their generators. Okay, so that's the initial algebra. We now discuss product sigma algebras. And this definition will be based on initial sigma algebras. So again, consider an index family of measurable spaces for all I in the index set. Now, the product of these sets x sub I is defined to be the set of all functions on the index set to the union in such a way that the value of x sub I is in x, capital X sub I, all I in the index set. Okay, so this might be a weird definition of a Cartesian product of sets, but you can see that this coincides with the case where you have only a finite set I. Okay, so this definition is consistent for Cartesian products of a finite set of functions or a finite collection of sets. Now, remark, if each x sub I is non-empty, then it can be shown from the action of choice that this Cartesian product is also non-empty. Okay, so there's a function from the index set to the union. In fact, it can be shown that the action of choice, so here we have seen that the action of choice implies the non-emptiness of the Cartesian product. In fact, they are equivalent. And sometimes this is called the axiom of products, meaning the first statement here. So we will not deal in detail with that set theoretic aspect, but the axiom of products, that is the statement here, is equivalent to the axiom of choice. So this is sometimes called the axiom of product. So this guarantees the non-emptiness of the Cartesian product of an arbitrary collection of sets. So following the notation for sequences, okay. Suppose I have a function x in the Cartesian product. Instead of denoting the value by this x sub I, we use a subscript. And we denote the function by this notation. So this mimics the notation in terms of sequences. So instead of function evaluation, we use a subscript, okay, where I, for instance, is the set of positive integers. So this will be our notation so for functions in the Cartesian product. Now, with this, we can now define the product sigma algebra on X, or I should say on the Cartesian product. So here we denote the product sigma algebra as follows. So the circle product, or O times. This is defined to be the sigma algebra, initial sigma algebra, generated by the projection maps. Okay. So let me define that one. So where pi sub j. So this is a function on the Cartesian product to x sub capital J. It's the projection map defined as follows. So I take a function in the Cartesian product, and we used our notation a while ago. This maps to the jth coordinate. So according to, of course, the definition here, so x sub j is an element of capital X sub j. So this map is indeed well defined. So again, the product sigma algebra, denoted by this notation, is the initial sigma algebra generated by the projection maps. So in terms of generators, so suppose that E sub I generates the sigma algebra sigma sub I for all I in capital I. Now, if I have an element E sub I in the generator, then the inverse image can be written as the following Cartesian product. So here, you take the Cartesian product over all indices except I of x sub j cross E sub I. So to have or to visualize this, let's say, inverse images of projection maps, let us consider the following illustration in the case of two sets. So here, our index set is 1 and 2, or the set containing 1 and 2. So if I have a subset E sub 1 and x sub 1, that is the horizontal part, or horizontal axis. So we want to determine all points in the Cartesian product. So you think of this as the rectangle that is mapped to E sub 1. That is when projected to x1 will belong to x sub 1. So the set of all points that will satisfy this property will be this shaded region here. So this would be the inverse image of the projection pi 1 of the set E sub 1. And an analogous manner, so if we have here a set E2, a subset of x2, we want to determine, okay, the set of points that when projected to x sub 2 will be in E sub 2. This will be this set, this shaded region. Okay, so you can write here the inverse image of the projection phi1 on E1 as E1 cos x2. And similarly, here, pi2 inverse of E2 is equal to x1 cross E2. So take note here, we have the set E1 and E2. And the other coordinates, you just take the whole set. So analogously, that is what is happening here. So we take this, okay, and then take the Cartesian product except the ith coordinate. Okay, if we denote E sub capital I, that's the index set, to be the collection of all these inverse images. So I here is in the index set, and E sub I is in the generator. Then by applying our previous theorem, we can conclude that this collection generates the product sigma algebra. So, by the previous theorem. So therefore, we can generate the product sigma algebra by collecting all the inverse images of the projection maps applied to the elements of the generator. So this is for an arbitrary Cartesian product. Let us now concentrate on a finite, the finite case. This will be the content of our next theorem. Let's consider an integer greater than 2 and a family of measurable spaces for k from 1 to n. Suppose that for each k, I can find a sequence, let's say, a countable sequence, AKM, which is a subset of E sub k. Now, by the way, what is E sub k? E sub k is is a generator of sigma sub k with the property that x sub k is the union of this E sub km's m from 1 to infinity. Then the product sigma algebra k in from 1 to n is the same as the sigma algebra generated by the Cartesian products of the generators And this is the same as the Cartesian product of the sigma algebras. Okay, so here we have an alternative generator for the product sigma algebra. You can generate it by taking the Cartesian products of the sigma algebras, or more simply, you can take the generators. Okay, before dealing with the proof, I would like to remind here the definition of the Cartesian product. Okay. So for instance, in the case of the sigma algebra, this is what the set of all Cartesian products of a sub k, k from 1 to n, such that a sub k is in sigma sub k. And similar definition for the case of the generators. Okay, so this is just the notation. So let us look at the proof of this theorem. So by, let's say, writing I to be the set of integers from 1 to n, sigma to be the Cartesian product of the sigma algebras, and let's say E, the Cartesian product of the generators. Okay. So in this way, we can write, according to the previous theorem, this is equal to the sigma algebra generated by A sub I. And this will be the sigma algebra generated by E. And this will be the sigma algebra generated by sigma. Okay, so here we just introduce some notations so that we have a more simple, or more we have more simpler expressions. Okay, so let's start with the following note. Note that we can write the inverse image of the projection of E sub I. What is this E sub I? Of course, for E sub I in the generator and I in capital I. This is the same as combining m from 1 to infinity all the following Cartesian products. So you take all indices except I. So this is a finite Cartesian product. AKM cross E sub I. Here, this follows from our assumption here. Okay. So you replace x sub k by this union, and you have, and then you apply the associative property of products. Okay, so here you can notice that this is in E by the definition of E. So this one is indeed now an element of sigma of E. Okay, thus this set, recall that this is just the collection of inverse images of projection maps. So this is a subset of sigma of E. Okay, and so the sigma algebra generated by E is a subset of, or E sub I is a subset of the sigma algebra generated by E. Since E is a subset of sigma, we have also this one. Okay. So to show that all these three are equal, next, the next step is to show that the largest among these three sets is also a subset of the smaller one. And from this, you can see immediately that all of these three must be the same. So for this, let's start with an element of a sigma sub I. Then the product is, well, you can check that this is the same as the intersection of pi inverse E sub I from 1 to n, or I in capital I. To get that, okay, so if you take the intersection of these two, okay, so let us extend, for instance, E sub 2 in this way. So if this is E sub 2, okay, let's just superimpose that one here. So you see that the intersection of the two regions is basically this one here, and this is E1 cross E2. So you can write the Cartesian products of sets as intersections of the inverse images of the projection maps. Okay, so that is what we did here. So the Cartesian product, the one on the right, on the left, is the intersection of the projection maps, inverse images of the projection maps. And each of these is in E sub I by a definition. So the finite intersection, okay, of elements in E sub I must be in the sigma algebra of E sub I. And by a straightforward calculation, and I will ask you to verify this one. Leads to the following. So we can also replace the generators by the sigma algebra. And you can see that, okay, this is of course sigma. The sigma algebra generated by sigma must be a subset of the sigma algebra generated by E sub I. So once you have verified this, it follows immediately that we have this inclusion that will establish the equality of these three here. So once again, assuming that each x sub k can be written as a countable union of elements in the generator, The product sigma algebra can be generated by the product of the generators. That is the content of this theorem.